Welcome to part 8 of my online probability course. We're going to be talking about probability density functions, and the key point here is that we care about, when we're writing a function, we care about mapping all possible outcomes to their corresponding probabilities. So we're going to start out with an event set, and capital X is going to represent all the possible outcomes. And we're going to use a lowercase x because these lowercase x's are going to be the individual outcomes in our probabilities space. And we want to write a function, p of x, that's defined for every single probability in the space. And then the function will have these three properties. All the probabilities will be greater than or equal to 0, and they'll be less than or equal to 1. And importantly, when I add them all up, when I add up all the possible probabilities corresponding to all the possible outcomes in the probability space, I should get 1. 100% of the things should have, the probabilities should add up to 100%. We just talked about one of the 4 important discrete PDFs we're going to be talking about. So when I say PDF, I'm referring to a probability density function. They also are called probability mass functions in certain textbooks. So if you see PMF, that's what they mean. But it's a little more common that you'll see probability density functions, PDFs. And we already talked about these. We didn't put it into a PDF, but we talked about how to calculate all of these probabilities. So I'm not going to focus on that one quite as much as the next 3. We have hypergeometric. Hypergeometric relates to drawing cards from a deck, that type of thing. Geometric pattern, a geometric series is something like 1/2, 1/4, 1/8, 1/16, and so forth, where even though there may be infinite terms, they add up to 1. And then finally, the negative binomial, which is a generalization of the geometric pattern. So I've got some examples of these, and I'd like to start by taking a look at example. I'm going to show this example in a minute, example 1. This chart will appear again at the end, and I'll go through it. There are formulas for these. I don't really want you memorizing formulas and how to put it all together. I think that it's easier to see the ideas and to work through the problem solving of how this stuff arises, and then to use this as a review. I think it makes a lot more sense as a review than as a way to try to learn. So let's launch into the first example we have. As you may have realized by now, I prefer examples that are a little bit quirky or funny or silly. And instead of the more textbook examples, which will be related to real world situations like a manufacturing plant with a machine that's filling water bottles to a certain tolerance, or widgets making widgets, or some kind of insurance actuarial situation. And yes, those are legitimate questions. Those are real world situations, but they can be dry as soda crackers. So I try to spice things up. So I had my kids help me with some of the examples here. So those of you who grew up going to Six Flags in the summer may recognize this situation where when you're riding acrophobia, it drops into free fall and all of a sudden somebody launches the F-bomb. And in this situation, the kids are tall enough to ride the ride, but not really ready for the F-bomb. So we're going to so we have a fixed probability, that's what we need. The probability of the F-bomb is 30%. It's going to happen 30% of the time. We're going to say that's exactly 30% and it's fixed. And then we're going to let this x be the random variable, which is the number of times they ride acrophobia before the dreaded event occurs. Okay, so the different values for x are the first thing we want to think about, right? And x could be 0, right? On the very first time, if somebody drops the F-bomb, then, right, this is the number of rides before the dreaded event occurs, well, 0 if it happens on the first one. Or they could ride the first time and nobody drops the F-bomb, and then the second time they do. So we're going to create a T-chart. We're going to list all the possible things that can occur in the event space. Then we're going to calculate a few of the individual probabilities, and then we're going to see if we can find a pattern and then be able to write a closed form version of P of X. Okay, so let's switch to the tablet and see if we can manage that. So in the summary chart I just showed you, we have P is the probability of success, so P equals 0.3, Q is 1 minus P. So the probability of failure, it's kind of ironic that the F-bomb dropping is the success. But again, all of these probability density functions, they have a particular event that they're looking at. So we tend to call that a success, right? The particular item that I'm looking at. So let's create a t-chart. We're going to have X on the left and the probability of X occurring on the right. Oh yes, and I said that we should consider what the values of the probability space are. So let me, in green, we'll show that X is equal to the set. Well, it could be 0, we said, right? If the F-bomb drops immediately, or they could get 1 ride in and then the F-bomb would drop on the second, or they could get 2 rides in, ... So X is the number of rides, successful rides, before they end up hearing the F-bomb. Okay, so here, when we say X equals 0, this is the probability that the F-bomb is dropped immediately. They have 0 successful rides. Oh, I guess I did have success defined properly, right? Success is number of rides. Success is a ride without hearing the F-bomb. So if they go 0 rides without hearing the F-bomb, that means that we had a failure. So that probability is going to be 0.7. All right. And then the probability of having 1 ride success, which will be a 0.3. Then the second ride is a failure, so 0.7. So you can see these probabilities are always going to end in a 0.7, right? When I have 2 successes, that means that I'll have 0.3 times 0.3, so I'll have a 0.3 squared times 0.7 to the first power. So you can see how this is working. Let me do one more. So what's the probability that there are 3 straight successes? Well, those successes are 0.3 and we need 3 of them, so we raise them to the power of 3 and then multiply by the failure. The failure always has to happen in that 4th slot or we're in a different place. And just notice that this chart can continue going, and hopefully you've seen the pattern because there's a relationship between these numbers and these coefficients, right? So if I can follow this pattern, then I should be able to write a closed form version of this function. And so the probability of X successes before we terminate is going to be 0.3 raised to the X times 0.7. And notice that this term does work if I apply it. The pattern works regardless, right? Because 0.3 raised to the 0 would be 1. So this is the correct probability density function right here. This is the closed form. This is what I've been asked to find. And now you just tell me the number of successes, like 22, and we can put in 22 for X and calculate the probability that the kids get to ride 22 times before they hear the F-bomb. It's going to be a very small probability. I would like to point out, if we go back up here, why I was using the ... This termination this termination criteria is possibly infinite. In other words, you could keep hitting success after success after success infinitely many times. It's possible, it's extremely unlikely, but that's why I didn't use a 1 to n when I was talking about the summation, when I was talking about these PDFs, right? It could be possibly infinite. So now you've seen the process. Let me sort of summarize what we're going to try to do. I think the best way to sort of understand the flow and the logic of these 4 distinct probability density functions is to make this t-chart, right? First of all, we're going to determine all possible values of the random variable, so we'll know whether there's a finite number of trials or whether there's a possibly infinite number of trials. Then we're going to create this t-chart looking for this pattern, and we're going to calculate a few of the probabilities, and if we can discover the pattern, then the probability density function should be easy to write. Then we write it in closed form, and then we're going to try to identify these as one of the four types. And the one we just did was geometric, right? We had this geometric series. If we go back, if we go back, we have this geometric series where, right, this is A, and then this is the R, right? So I have, we have the leading coefficient of the geometric series, which is 0.7. It's in all of the terms, and then I get the next term by multiplying by the common product, right? The 0.3. So we can sum up this geometric series as needed. So that was geometric. We're going to learn these others. So now we've done binomial and geometric. We'll see the others. And while we're doing this, to determine which of the four it is, we're going to ask a couple of key questions. First of all, are we drawing with or without replacement? So when we're drawing, you might want to jot this down in your notes. When we're drawing with replacement, that's hypergeometric. And without replacement is the other three. Okay, then our second key question is the termination criteria finite or possibly infinite? Well, the finite ones are hypergeometric and binomial, and the two possibly infinite ones are geometric and hypergeometric. And so with those two questions, we can differentiate everything except for geometric and hypergeometric, but hypergeometric is an extension of the geometric. So hopefully you'll see the pattern, the relationship between those two. So let's try this process on a couple more examples. So the next example we have relates to Halloween candy. Sorry, Halloween candy. And what's happened is the grandparents have taken the kids out for trick or treat, and they just have way too much candy when they get home. So this college professor does what any good parent does. She confiscates a bunch of their candy and takes it and gives it to her college students, right? But the problem is she does allow them to get some of their favorites, and so when she confiscates, there's a bunch of bad candy, right? So out of the 40 pieces of candy, when Renata gets to choose, 25 are bad, 15 are good. And so now Renata wins this prize in her college class. She's done something good, like answered a bonus question or something. And so she gets to choose from 40 pieces of candy. She's going to get 5 chosen at random because the professor knows all the bad candy will just be there at the end, right? So you have to randomize it, so you give away some of the bad candy with some of the good. Not that I've ever done this in class or anything, but if you were to do it, you'd want to give them away randomly, right? So we're going to let the lowercase x are going to be the number of good pieces of candy out of the total, which will be 5 pieces of candy that she gets. So we've got a partition, right? So hopefully this was obvious to you when we started looking at this, that we have 2 subsets. We have the bad subset with 25 elements in it, the good subset with 15 elements. Before we make this t-chart though, let's make a note about x. So the probability space, well, if we're talking about number of pieces of good candy, then she could get 0, right? It would be unfortunate, but she could have 0 pieces of good candy, 1, 2, 3, 4, and if she gets extremely lucky, Renata could have all 5 of the pieces of candy she randomly gets come from the good side of this partition. All right, so now the probabilities here change a little bit. So it's interesting if, well, let's just do it. That thought should remain incomplete because it wasn't very good. All right, so I'm going to create my t-chart with x on one side, and we probably need more room here, and then p of x on the right. And let's just start with 0. We know that if she gets unlucky, Renata could get 0 good pieces of candy. All right, and then how would that happen? Well, that would happen if she ended up with 5 from the bad side. All right, she could end up with 5 from the bad side and 0 from the good side. So in this type of situation, this is in this hypergeometric pattern, I use choose notation to pick the 5 pieces of candy here. And then there'll be 40 choose 5 possibilities. So this is going to be, she gets all bad candy, so it's 25 choose 5. And I'll put this in, right, the 15 choose 0. She gets 0 of her choices come from the good side of the batch. And then the total number of choices that are possible is 40 choose 5. Okay. Well, the pattern isn't perfectly clear yet. Let's do it for one piece of good candy. Well, if she gets one piece of good candy, then Renata has gotten 25 choose 4 bad pieces of candy, and then 15 choose 1 good pieces of candy, and still this denominator is 40 choose 5. Okay, so maybe the pattern is getting a little clearer. Let's try for 2, right? So if there are 2, there's 25 choose 3 bad pieces of candy and 15 choose 2 good pieces of candy over this same denominator of 40 choose 5. Okay, and I'm running out of screen space, so let's say we can figure out the relationship between x and this function. It's right here, right? This is the number of successes, and this is the number of failures, which is 5 minus the successes. So I have successes, 5 minus successes. The total number being drawn is in the denominator, and it doesn't change, right? This is 2 successes relating to the 2 over here. So let's try to write this probability density function. So we have p of x, I don't know that I'm going to have room, let me try hard, is going to be 15 choose x times 25 choose 5 minus x all over 40 choose 5. Now in this hypergeometric pattern, a couple of things are important. So if we look at a whole term like this, right, notice that I have 2 binomial coefficients in the numerator, and the top numbers, the 25 and the 15, add up to 40. And then the bottom numbers in the binomial coefficients in the numerator, 5 plus 0, they add up to the bottom number in the denominator. So that's what we mean by this is what I mean when I say the hypergeometric pattern. I mean this binomial coefficient times binomial coefficient divided by binomial coefficient, where the numbers in these binomial coefficients match up, right? So when we write a hypergeometric probability density function, we're going to have the same thing happening, right? The 15 and the 25 add up to the 40, and then the x plus 5 minus x, well, x minus x is 0, so the 5 is going to be what's left over when I add them up, is going to equal the 5 in the denominator. So this is the hypergeometric pattern for individual probabilities, and this is what a hypergeometric probability density function looks like. Okay, so now we have a situation where a gambler is going to keep betting on odd until it pays off. plain roulette. And it's important to know whether it's American roulette or South American roulette. So American and European roulette wheels are slightly different than South American. And the American roulette wheels have numbers 1 through 36, and they have a 0 and a double 0. So in South America, I don't really remember. I know that they're different in different locations. I'm pretty sure that South America, they just have the 0. So there's only 37 total spaces rather than 38. But be that as it may, he's going to bet on odd. So here's what happens, though, just so you know how the game works. The probabilities are set up, the payoffs are set up as though there are only 36 slots, right? So half of these 36 would be even, half of these would be odd. So you'd think that half the time it would come up odd. The reality of the situation is, though, it only comes up odd 18 out of 38 times. So the probabilities are out of 38 possible outcomes, but they pay off as though they were out of 36 outcomes, which is how the house makes money. The house makes money on those extra, that extra large fraction in the denominator. But that doesn't really matter for what we're doing. All we have to do is figure out the probability of getting an odd. Well, 18 of these 36 are odd out of 38 possible, so the probability we're looking at is 18 over 38, or 9/19. Okay, so now we want to write a probability density function where x is the number of spins until the wheel comes up odd. Okay, and it could happen at 0, right? The very first time we could have an odd, or we could have when x equals 1, that means we had to watch, a non-odd number go by and wait one time, and then on the second time we had an odd. So let's set this up on our tablet. So our chance of success, right, there are 18 successes out of 38 possibilities. So 9/19 is P, our probability of success. Okay. And what can our event set be? Well, we can have a 0, we could have a 1, and this is a theoretically infinite probability space, because we could keep hitting even, or 0, double 0, even, double 0, even, 0, even, forever and ever, and never actually terminate. So this is a theoretically infinite one, which which means it can't be hypergeometric, for example. And so let's just look at the probability of of having the stopping criteria occur on the very first time, right? Well, that would mean that this probability is 9/19. What's the probability that we have a failure and then a success? Well, that's going to be 10/19 for the failure times 9/19 for the success. And then what's the probability of 2 failures before the eventual success? Well, that's going to be 10/19 squared times 9/19. And hopefully you can see that this is a geometric pattern. And the power of the 10/19, that's the number of failures we have before there's an eventual success. So the probability density function in closed form is 10/19 raised to the x power, and then that final success occurs and stops the process, right? So this is our closed form. What makes it geometric? Well, it's geometric because it has this a sub 0, right? This leading term, and then it has this common product, right? I get from one term to the next term in line by multiplying by 10/19. So again, this is geometric, a geometric PDF. Stop. We're back to the theme park where the F-bomb drops 30% of the times acrophobia does. And suppose the dad in this example, instead of the first time he hears the F-bomb dropping, he takes the kids away. Now he's going to let it go 3 times. And you know, it's okay, we'll ride it a while. And if the kids get lucky, we might be able to ride it 20 or 30 times before the F-bomb is dropped 3 times. But that's the limit. And if they're unlucky, they'll only get 3 more rides. So how many rides do the kiddos get? We're going to let the random variable x be the total number of rides, right? So if they get, let's just say they had 5 clean rides and 3 F-bomb rides, right? That would be a total of 8. So x would be 8 in that instance. So let's think about what the variable x would look like. So what values could x possibly take on? Well, remember, we're talking about total number of rides. So there have to be at least 3, right? So the lowest number is 3. But then if they had 1 clean ride before and 3 F-bomb rides, right, that would be 4 and then 5 and then ... Okay, so instead of starting at 0 here, we're starting at 3. Let's see if we can calculate this probability. Well, the probability of exactly 3 rides, well, they're all failures, right? So these are 3 straight F-bomb rides, so 3 cubed. Okay, now if they get 4 total rides before Dad takes them away from the park, that was, that is 0.7 times 0.3 cubed. Those are the probabilities, but let's think about this. If we're looking at the pattern, and then I'll put F here for fail, or the F-bomb, however you'd like to think about it. But whatever they're doing, right, however this pattern turns out, there has to be a failure in the final slot, or it wouldn't have triggered the stopping, right? So then the question becomes, out of these 3 spots, where does the S go? Right? There is a success, there is a clean ride somewhere in here. And so the number of ways this is possible is 3 choose 1. Right? Out of the 3 possible slots over here, I'm picking 1 for the S to go in. And if I've picked the S to go in the first slot, then we'd have an F and another F, or F-bomb, right? And that would be how it finished. So the S could go in any one of these 3 slots. So I have 3 choose 1 times 0.7 to the first power, that will help us discover the pattern later, times the 3 F-bomb rides at 0.3 raised to the 3rd power. Okay, so what about 5 total rides? Well, with 5 total rides, they've had 2 successes, so the probability of success raised to the 2nd power, and there are 3 fails. And again, let's think about this pattern, right? So now there are 4 rides before the final fail, right? So it ends with a failure. But now in these 4 places, we get to put 2 S's, for example, like this, right? Well, there are 4 choose 2 ways to pick those successes. All right, and going on with 6, you can see that we would have 5 choose 3 times 0.7 cubed times 0.3 cubed. So hopefully it's become clear, right, what these relate to. And I've chosen kind of badly with my x variable, so these are going to be off a little bit. I think what I want to say is that we often choose x so that x is the number of successes before the third fail. So a lot of times we would try to set up x where it starts at 0. And that would have made the notation a little bit cleaner. I will try that in just a moment, but we can write this PDF this way. That's not a problem. It's just going to be slightly messier. So let's do it in blue here. So this probability of x, right? Well, what's the relationship between these numbers and the choose notation? Well, the 3 is 1 less than 4, and the 1 is 3 less than 4. So what I'm doing is I'm choosing x minus 1 over x minus 3. Excuse me, x minus 1, choose x minus 3. Notice that also works here. X minus 1 is 4, and x minus 3 is 2. So the 4 choose 2 is also follows this pattern. And then I take the probability of success raised to the number of successes pattern, but the number of successes is x minus 3. And then I always have the 0.3 to the 3. So this is fine. This is a proper probability density function, but just notice that we could have done this a little more cleanly. It looks a little better if we switch this to being 0 and 1 and 2 and 3. Then notice what happens. My probability density function here is P of x equals x plus 3, choose x, times 0.7 0.7 raised to the x power times 0.3 cubed. So that all depends on how you define your capital X set. And this is probably a little cleaner. I would suggest this one. And you can see the relationship here between the number of successes power goes with the probability of success. And then you have 3 choose 1 ways to place the success. Or you have 4 choose 2 ways to place 2 successes in these 4 slots. So sorry, I kind of headed off on the wrong direction, but in green is the way the problem is written, and in red is the way we probably would have preferred to do it had we chosen our set X a little more elegantly, so that the problem turned out a little more elegantly. So let's take a look at the chart that summarizes these 4 common discrete PDFs. Now I've placed a full page version in the unit, so you can find that on D2L. But let me just tell you about what I think is important here. So the way I diagnose which type of pattern I'm using, and by the way, that last one was negative binomial. I think I said that. But the first thing I look at is whether or not the draws are with replacement or whether they're without replacement. And 3 of them are with replacement. The binomial, the geometric and and the negative binomial are all with replacement. So as soon as I see a situation that's without replacement, then I'm guessing it's hypergeometric. It may be none of the patterns, right? You can have a discrete PDF that's not one of these 4 patterns, but if it is one of these 4 patterns and it's without replacement, then hypergeometric is our option. The other thing I'm looking at is the criteria that terminates, right? So with hypergeometric, there's a finite number of draws, and with Bernoulli trials in the binomial theorem situation, there's a finite number of trials. So if I have a finite stopping criteria, a finite termination criteria, then I'm either using hypergeometric or binomial. And then if I have a possibly infinite termination criteria, then I'm either using the geometric or its generalization, the negative binomial distribution. So I've given some kind of canonical examples of these and the sort of mathematical description and formula. So this is a really helpful chart, again, to review, especially prior to tests and quizzes. But most of these, if you go ahead and put together a t-chart and start calculating the probabilities, usually starting with 0, because 0 tends to be a pretty easy one, but you usually need 1 and 2 to kind of see the pattern. So with 2 or 3 of well-chosen probability calculations, you can usually determine the closed form, even if you're not quite sure when you start out which of the 4 it might be. So let's use those stopping criteria we discussed, those 2 questions, the with or without replacement and the stopping criteria, to determine what's going on here. So this is a situation where there's a swim meet, and any of you guys who have swum competitively know that it's pretty likely that your goggles will come off. And if they end up in your mouth, you can't drink, you can't breathe, and you also can't see, right? So the problem is you can't fix it because in a competitive meet, you'll get DQ'd, and that does not mean Dairy Queen after the meet. That means disqualified. And anyone who has done swim team competitively has been in that situation where the goggles came off and you have to try to finish the race. So we're going to assume that that happens 10% of the time. All right, so these are draws with replacement. Why? Well, because we have a fixed probability of success. So the draws are with replacement. We have the same probability every time. Now the question is the termination criteria infinite or possibly infinite, or is it finite? Well, here it's finite. This is for the 6 events that she is swimming. So there could be 0 malfunctions, 1, 2, 3, 4, 5, or 6 malfunctions. So when we have with replacement, let's just jump back up here to the chart. So in this particular example, we have probabilities with replacement, but we have a finite stopping criteria. Well, the only other finite stopping criteria is hypergeometric that has without replacement. So we know after just checking the stopping criteria and whether or not it's with or without replacement, we know that it's a binomial distribution. So that's what I wanted you guys to understand. Let's go ahead and put this PDF together. And since we've already done binomial theorem in the last video, this shouldn't be all that surprising. So I will write the t-chart. So the probability that it happens 0 times. Well, remember that, actually, let me use k. So with with the binomial theorem where x is our probability of success, I've been using k. So let's say k successes and the probability of k successes. Well, the probability of 0 successes is going to be 6 choose 0 times the probability of success, which is funny. It's actually the malfunction is the success. So 0.1 to the 0 times 0.9 to the 6th. Well, both of these terms, both of the first 2 terms are 1. So this is just 0.9 to the 6th. The next term we have 6 choose 1 successes. So I have 0.1 to the 1st power times 0.9 to the 5th power. And for 2 successes, we would have 6 choose 2 times 0.1 squared times 0.9 to the 4th. So like before, we have the number of successes, so it's the total number of trials, choose the number of successes, the probability of success raised to the number of successes power, and the probability of failure raised to the number of trials minus the number of successes power. Okay, so to write this one, we have probability of k, right? I'm using k instead of x. We will have 6 choose k times 0.1 to the k times 0.9 to the 6 minus k. All right, and you probably could have written that down without the t-chart, but I always like putting the t-chart there. Then I can go back and I can compare my terms in the t-chart and make sure that everything is coming out correctly. Now this is a slightly different example. Let's take a look at the difference here. So we still have Dakota swimming. She still has this fixed 10% chance of diving into the pool and losing the goggles and them ending up in her mouth. But now look at what the random variable is. The random variable is the number of times Dakota dives this season before she ends up choking and blind for an entire race. Okay, so notice now, let's just go back up to the chart, right? Notice now that we have a possibly infinite termination criteria, right? It is possible that she could never have the goggles come off, even though there's a 10% chance. It doesn't mean that on any one time, it doesn't mean that she couldn't go 10 times in a row or 20 times in a row without the goggles coming off. Okay, so we have an infinite termination criteria, and so the only choice is whether or not we have geometric or negative binomial. The difference here is that it only takes one failure to trip the termination here, and here it'll take multiple failures. So let's go back and take a look at whether this is geometric or binomial, right? And you can see that this is the number of times she dives a season before she ends up choking and blind for an entire race. This is just once. So this is a geometric PDF, and we've already done a couple of those so far in this in this video, so I'm going to stop it there. The only thing I want to point out is these are the 4 that we'll use, and these 2 columns here, the draws, how the draws happen, and how the termination occurs, is the way you're going to tell 3 of the 4 of them apart. And remember that negative binomial is just like geometric, except like with the F-bombs, one F-bomb ending the rides on acrophobia was a geometric PDF, and then having multiple F-bombs be the stopping criteria, in our case 3 F-bombs being the stopping criteria, was a negative binomial distribution. And the big difference there is we have the choose notation. We have the binomial coefficient in front of the powers of P and Q. Okay, so that's it for the discrete PDFs. Make sure you do your completion quiz, and good luck.